Let's close out this chapter by looking at a little bit more about the currents in the low latitudes, and we will go for that to our sphere balance again. Ocean wind, if you think about the trade winds and the westerlies, then the zonal derivative of the meridional winds is much smaller than the meridional gradient of the zonal wind. So going from the easterlies to the westerlies, the meridional direction, the zonal winds change a lot compared to how much the meridional winds change in the longitudinal direction. That allows us to write the sphere balance going from minus d0 to 0 of rho 0 v dz. Which was 1 over beta del tau del x minus del x del y. This is why we are worrying about the zonal gradient and the meridional gradients. This is the curl tau over beta. So here we can simplify this to meridional transport as approximately minus 1 over beta del tau x del y. For simplicity, we're going to use this to derive the currents and the countercurrent. So using the assumption that the vertical velocities at the surface and at the level of no motion are zero, which we already did, the continuity equation can be written integrally as du bar dx plus dv bar dy equal to 0, or write in terms of transports dm bar x dx plus dm bar y dy equals 0. So using that relation, we can write dm bar x dx as minus dm bar y dy. So we have squared up coming in here. We will write beta as 2 omega cosine phi divided by a. Okay, so the meridional projection of omega divided by the radius as the approximate derivative. That is written as del tau x del y tan phi plus del squared tau x del y squared a. So that's just simplification of the this equation. And oops, where was I? Yes. So this term is small at low latitudes compared to this term, which allows us to integrate from the eastern boundary towards the west to get the transports in the zonal direction. We're trying to compute currents given the wind stress, and that's what we'll end up doing. So m bar x in this case is minus delta x over 2 omega cosine phi, okay, times average dtx dy tan phi plus a d squared tau x dy squared. So this has been integrated in the zonal direction. We have integrated out the dx, so we are integrating both sides, which is approximately equal to minus delta x a. So drop this term because it's small for a small phi, and write it as this expression here. So given the wind stress and its meridional derivative, we can compute the zonal currents or zonal transports, and of course also the meridional transport as a over 2 omega cosine phi integrated zonal meridional derivative of the zonal winds. Okay, not a very difficult thing to do, but when you do this, you have observed currents looking this way. You have south equatorial currents with maximum speeds in these colors. On the equator you get a minimum because of the upwelling and the wind convergence happening in the ITCZ, and you have equatorial countercurrent or the ECC arising here. In a simple undergraduate course, we say that the winds are pushing the water, piling them up here, so you have down gradient flow happening. But in a Schroeder balance, that happens where the wind stress curl goes to 0. And then you have here the north equatorial current, which is at the core of the northeasterly trades. What do you get with the simple formulation we derived here? You see that you need a boundary condition. It's a one-dimensional equation, so you can only set one boundary condition. So you can set mx to be 0 at the eastern boundary and then integrate westward. So here is the wind field. You have doldrums, northeasterly trades and southeasterly trades, and then you get the d squared tau x dy squared term given this way, and the ocean currents that result from integrating that equation for mx gives us north equatorial current, equatorial countercurrent, and the south equatorial current. Okay, because Swerdrup balance has a beta, you can integrate it at the equator, and it gives you the equatorial countercurrent as well. Fantastically simple and dynamically useful, but of course it has all sorts of limitations as well, such as only one boundary condition being applied. The last remaining piece is the equatorial undercurrent, starting with our favorite equations again. At the equator we are blowing winds from basically east to west, so you can think about the balance in the zonal direction as building up this pressure gradient that we talked about, water being piled up on the west with the wind stress blowing, and some dissipation term, dsu. Okay, so the balance can be that dsu is balancing the pressure gradient so that the winds just accelerate the zonal currents. But what happens is you actually get piling up of the water and higher sea levels on the west, and below the surface you get actually a eastward pressure gradient, and there is a coherent current running like a ribbon from the western boundary all the way to the east, which we call the equatorial undercurrent. You can see the surface currents here being westward and the strong eastward current, and if you imagine moving eastward, Coriolis will push to the right in the northern hemisphere, to the left in the southern hemisphere, so you can maintain coherence quite far eastward. The actual calculations are much more complicated, especially in terms of explaining the strength of the undercurrent. You need nonlinear advection terms of the relative vorticity and so on and so forth. But Joe Pedlowski started writing beautiful linear theories for the equatorial undercurrent in the 1970s, and essentially you can think of the wind stress at the equator creating this pileup of water and eastward pressure gradient, which drives a subsurface equatorial undercurrent. So that's the story of this chapter, which is kind of long but a lot of beautiful, elegant, important concepts which we will now try to apply to various situations of tropical dynamics of the atmosphere and the oceans.